All right, so we'll get started. We'll have exam one on Wednesday. Okay, so 2 days from now. Um, Today's classroom disinfection is assigned to Marcus and Morgan. All right. So last time we talked about thermodynamic systems. So basically, the system that you are interested in, their thermodynamic properties, it's called a thermodynamic system. So you can have a closed system, you can have an open system, depending on the if they are having like boundaries, or if they are having like heat exchange or something like that. If this is a well insulated, then it's called a closed system. If it's a kind of open system to the surrounding, direct in contact, then it's called an open system. Okay. All right. And then we talk about the for a system that is doing work to the surroundings. So basically, you can use start from here, looking at the small change in the volume corresponding to the temperature, the work done by the system to the surrounding, and then you can do integration from its initial volume to final volume. Okay, PdV there. P is pressure. For the internal energy of the system, if you just consider the kinetic energy, meaning just the motion of it, you are not considering any potential energies or interaction between molecules, then it's 3/2 of kBT for each molecules. For the system, then you multiply by the number of molecules you have. So then it's 3/2 of nRT, and it's in moles, okay? Or in this expression, but it comes to here. If you combine Avogadro's number and then Boltzmann's constant, okay, that gives you gas constant R. All right. And then we talk about the first law of thermodynamics, but before that, we pretty much just gave out the zeroth law of thermodynamics. This is straightforward. So if you have two objects in contact, A and B, and they are in equilibrium, but in the same time B is in contact with C, they are in equilibrium, then A and B, A and C, if you put them in contact, they should be already in equilibrium. Okay, so mathematically, straightforward, T1 equal to T2, T1 equal to T3, then T2 equal to T3. Okay. Then the first law of thermodynamics is basically the energy conservation. So change of internal energy of the system equals to the heat change minus the work done by the system. Okay. In differential equation form, as derivative of internal energy equal to derivative of Q minus derivative of the work. All right. So that's first law of thermodynamics. Sign conventions, if heat is added to the system, then Q is greater than 0. If heat is removed from system, Q is less than 0. Okay. Work is positive if it's done by the system to the surrounding. Work is negative if it's done by the surrounding to the system. Okay. Or done on the system. We took a look on several thermodynamic processes. So isobaric means constant pressure. Isochloric, that means constant volume. Isothermal means constant temperature. For adiabatic, that means no heat transfer. Okay. For a full circle of processes, that means if the system starts from one particular point and then going through a series of processes, but goes back to its original status, then the internal energy should be equal to 0 because it returns to the original status. Okay, in that case, Q is equal to W. All right, the heat change is equal to the work done by the system. All right. And then we also talk about the heat capacity for a gas system. So in that case, depending on what process is the gas system undergoing. So if you have constant volume process, then heat change is equal to more of the air of the gas times CV sub V, means the molar heat capacity of the gas system under constant volume process, okay, times change in temperature. And you can rewrite the equation, so CV molar heat capacity is equal to 1 over m Q over delta T, okay? And you have V as constant. All right. So if you have ideal monatomic gas, I think we took a look at this earlier in the previous chapter. So internal energy is 3/2 of nRT. That's basically you are just looking at the motion of the molecules. Okay. So if the volume doesn't change, then work is equal to 0. So then internal energy change is directly equal to the heat change. Okay. So in that sense, then heat change or heat change should be equal to 3/2 of nR times delta T. So then CV equals to 3/2 of R. Okay. And that's corresponding to the motion of the gas molecules in X, Y, and Z direction. So each component will add up to be like 1R or 1/2 of R, okay? So in that case, we can see there are three dimensions or three degrees of freedom for the motion of the molecules. Its motion in X and Y, Z directions, okay? So in that sense, if the gas, each molecule has, say, n numbers of free degree of freedom, then the internal energy or the in terms of this molar capacity, you can write in this way. Okay, if D equals to 3, then it's 3/2 of R. If you have like n D equal to 5, which is the case for the diatomic gas. Okay, so 3 degrees of freedom in X, Y, and Z, and then also plus the rotational degree of freedom, okay, 2 there. So then C sub V for diatomic is 5/2, okay. For triatomic, then it's 7/2, okay. So you add 2 more additional degree of freedom to it, okay. So for monatomic is 3/2, and then 5/2, and 7/2, okay, in that order. All right. So let's take a look on this one. It says professional divers sometimes use heliox, okay, which the components are 79% of helium. So this is in the place of the air we typically have nitrogen, okay. So now you're replacing nitrogen with helium, and 21% of oxygen, okay. That's by mole fraction. It says, suppose a perfectly rigid scuba tank with a volume of 11 liter contains heliox at an absolute pressure of 2.1 times 10 to the 7 Pascal at a temperature of 31 degrees Celsius. The diver goes down to a point where the sea temperature is 27 degrees Celsius while using a negligible amount of the mixture. As the gas in the tank reaches this new temperature, how much heat is removed from it? So helium is much lighter than nitrogen, so then the tank can be lighter than if you fill the tank with air, okay? So in this case, you need to have a little bit knowledge of the chemistry here. So for helium, all right, it's He. It's a monatomic gas. Okay, so it's only each molecule is just one atom itself. Now for oxygen, it's O2, so it has 2 atoms in a molecule. So it's a diatomic gas. So for a gas system, instead of doing the mass times heat capacity times delta T, the heat change would be moles of the gas times C. Okay, so in this case, the volume doesn't change, right? So for the gas tank, its volume wouldn't change. If you consume some of the gas, then pressure could change slightly, but volume should stay the same. So this would be the equation you wanted to use. Now in the system, you actually have two gas. Okay, so you probably want to do like C1, N1, CV1 delta T plus N2 CV2 delta T. Okay, so maybe you can denote like one is the helium and then two is the oxygen, O2. Actually, I think you can look up these two numbers, this one and this one. Okay, so CV1 for helium, or let me just write down CV helium here. If you look it up on the table here, so for helium it's 1.5 exactly. Okay, so that's 1.5. That means 3/2 times R. Okay, it's CV divided by R, so it's 1.5 but multiplied by R. For CV of oxygen, okay, that is 2.53. So you can use 2.53 times R. R is the 8.31. Okay. So I think you can work out for the temperature change because it goes from 31 degree to 27 degrees. So it's -4 degrees. Delta T is -4. You would need to know N1 and N2. Okay. Moles of the helium and then moles of oxygen. It gives you the fractions of the two. Now it gives you the volume, the temperature, and then pressure. So you can calculate what's the total moles and then calculate the moles for each, okay, according to their fractions. Let me give you guys a couple of minutes to work on this and then we can take a look at the solution together. You can use the PV equal to nRT for the total M. Okay, so let's take a look here together. So as I said, you can calculate the heat change, okay, how much heat change is by using this equation. So N1 is the moles for helium, and then CV1 is the molar heat capacity for helium, and delta T plus N2 moles of oxygen times CV2, okay, which is this guy, molar heat capacity for oxygen. Okay, we look those two up. We now need to figure out what's N1 and N2. Okay, so we can figure out the total M here first. So N will be equal to PV then over RT. Okay, so it gives us 2.1 times 10 to the 7 Pascal. For P, the volume is 11 liters. So you want to convert it into meters cube divided by R, 8.31. Okay, T, it's given as 31 degree initially. So 31, you want to convert it into Kelvin. Okay, so that's in Kelvin there. This is joules per mole times Kelvin. All right. So it will give you the total M as about 91.4 moles. Okay. Then N1 for the helium should be 79% of the total. Okay. So 79% of this 91.4 moles, that would be 72.2 moles. For oxygen is 21% times that. So 21% times 91.4, that would be 19.2 moles. Okay. Then we have the numbers we needed to calculate the total heat change there. So this would be 72.2 moles times 1.5. For R is 8.31 joules per mole times Kelvin. Times delta T will be 27 degree minus 31 degree. Okay, so minus 4 degrees. Plus 19.2 moles times 2.53 times 8.31. Okay, the same unit of joules, mole over moles times Kelvin, times 27 minus 31 in degrees. Okay, so then this would be minus 52.15 joules. Okay, roughly minus 5.2 times 10 to the third joules. Okay, so the negative sign means the heat is being removed from the gas. Okay, so so if your answer should be just the 5.2 times 10 to the third joules. Okay, that's how much heat being removed. All right. Questions you guys might have on this? All right. So if you are clear, we can move on to the next section. I'm talking about details of the heat capacities for ideal gas. Okay, so for an ideal gas, the first law of thermodynamics will be applied. So delta E internal energy change should be equal to Q minus W. Okay, and then for heat capacity, all right. So you can write Q as C delta T, where C is M times small c. Small c is the molar heat capacity. Okay, similar version like specific heat when we talk about solid. So N times C, or complete equation could be like Q equals to small n times C times delta T. Okay. But just take these two equations, you can rearrange, so then you can write C as, so basically replace Q in the first equation with C times delta T, then move the W to the other side. So delta T or delta E internal plus W is equal to C times delta T. So then C is equal to delta E plus W divided by delta T. Okay. So most commonly you will have either a constant pressure process or a constant volume process. Okay. So during those process, then the molar heat capacity or heat capacity can be written as C sub P, means you are having constant pressure process. So that would be, again, starting from here. For W, for a constant pressure is equal to P times delta V, okay, divided by delta T. For a constant volume process, the work done will be equal to 0 because constant pressure, that means delta V is equal to 0. So this is equal to 0. So then the second term will vanish. So you only have delta E divided by delta T. So you can look at these two heat capacity. So the heat capacity under constant pressure and then heat capacity under constant volume. You can see in general for constant pressure process, heat capacity will be larger than the constant volume process because it has an extra term of P delta V. Okay. So in general, Cp is greater than Cv, but this is for gas. Okay. So for solid and liquid, we do not distinguish between Cp and Cv because for solid and liquid, under pressure difference, their volume difference is very small, negligible. Okay. So even if you have a constant pressure process for solid and liquid, this guy is delta V is about 0. Okay. So then the two will be the same. So that's why we didn't talk about Cp or Cv when we are talking about solid or liquid. It's just C. Okay. Okay. So now let's take a look on the differential equation form. Okay, so for constant pressure, then you have Cp. So basically, you change those delta into derivative signs. Okay, so then Cp dt equals to dE plus Pdv. Okay, so in the previous equation here, you change the delta into d delta of energy, internal energy times P dV over dt. Okay, and that will give you differential equation form there. The same for constant pressure process. Okay, so then CV dt equals to the derivative of internal energy. Okay. So you can see derivative of internal energy is just equal to CV over dt. Okay, so if you replace this guy with this, then Cp derivative of T equals to Cv derivative of T plus P derivative of V. Okay. Or if you divide both sides by derivative of T, then it's Cp equal to Cv plus P times dV over dt. Okay. Now for ideal gas, you can always have this equation, ideal gas law, PV equal to nRT. So from this ideal gas law, you can do derivative to both sides. Okay, so derivative of PV should be equal to derivative of nRT. Okay. There are two variables on the left, P and V, so then it becomes two terms, VdP plus PdV. All right. There's normally just one variable on the right. Temperature will be the variable. Okay. N and R is the constant. N is usually the also constant if you just look at a particular collection or a gas system. Okay. So then it's equal to nRT. All right. Now, if you have a constant pressure process, dP will be equal to 0. All right. So then PdV is equal to nR dt. All right, you can rearrange the term. So PdV equal to nR dt. Let me write on the paper here. So starting from V dp plus P dV equal to nR dt, okay? If you are having a constant pressure process, so this guy goes to 0, all right? So you only have that. So then dV over dt, you move this to this side, okay? And then move this guy to the other side, because nR over P, okay? So then, now you take this up to, so take this to here, dV over dt is equal to nR divided by P, right? So P and P will cancel out. So then you can see that Cp equals to Cv plus N times R, okay, which is this relationship here. So in general, Cp is equal to Cv plus Nr, okay? For a constant pressure process, you will have this relationship, okay? Cp equal to Cv plus Nr. Right? So basically, oftentimes you'll be just given CV, then you can calculate CP, or the other way around. If you are given CP, then you can calculate CV because N and R are fixed. Okay. Now, that's the theory. We derive it from theory, right? From experimental results, this is what you get for monatomic gas. So CP is measured usually, so for this particular data, it's equal to 20.79, which is 5/2 of R, okay? And then CV is measured as 3/2 of R, okay? So the difference is 8.31, okay? For diatomic, CP is 7/2 of R, CV is 5/2, okay? And then the difference is again 8.31. And then for polyatomic gas, it's 4R and then 3R for CV, 4R for CP. So the difference again is 1R, 8.31, okay? All right. So CV dt equals to derivative of internal energy change, okay? So this is for constant volume process, okay? Now look at a monatomic ideal gas. The internal energy consists of just the kinetic energy only. So it's 3/2 of nRT, okay? So then CV is equal to 3/2 of nR. Now CP should be equal to CV plus nR. So that's 5/2 of nR. Okay, so this is for the monatomic ideal gas. All right. So if a problem tells you you have a monatomic ideal gas, then you realize that this C sub V should be equal to 3/2 of nR. C sub P should be 5/2 of nR. Okay. All right. So let's take a look on this example on the ideal gas. Monatomic ideal gas. All right. It says the heat capacity at constant pressure. So this is CV. It tells you CV is that. Okay. So basically, you can use the information to calculate how many moles of gas you have, because for monatomic ideal gas, CV is equal to 3/2 of MR, right? From monatomic gas. And this is equal to 49.8 joules over Kelvin. Given R is 8.31. Okay. You can calculate what's M. and that's part A. Part B is asking you what's the heat capacity at constant pressure of the gas. Okay, so B, you're looking for Cp. You know that Cp should be equal to Cv plus Nr. All right. And C is asking you what's the internal energy at 300 K. So 3/2 of nRT. All right. So let's see here. You're looking for M here. So basically you start from there. Okay, so N would be equal to 49.8 divided by 3/2 times R, 8.31. Okay. It should be about 4.0 moles. Okay, about 4 moles there. Or 3.99. All right. Now on this one, this will be just equal to 49.8 now, because that's CV plus 4.00 moles, okay, times the 8.31 joules per mole times Kelvin, which is about 83. Okay, and this guy, 3/2 of NR, that's basically this guy, right? So you can just put that number down, 49.8 joules over Kelvin times temperature. It says 300 T, 300 Kelvin. Okay, so the internal energy is about 1.49 times 10 to the 4th joules. Okay. Any questions? Okay. All right. So next we'll be looking at an adiabatic process for an ideal gas. Okay. So we'll start with the differentiation equation here. derivative of internal energy is equal to derivative of Q minus dV. And then because this is again an ideal gas, so you can always write the PV equal to nRT. Okay. So for monatomic ideal gas, this is the internal energy. Okay, so CV equal to 3/2 of nR. So then dq, which is CV dt, all right. Let me see over here. So when you take a look at the PV diagram, okay, so the dashed lines here, they are the isothermal process. Okay, so isothermal process here. And then if you have adiabatic process, you are going to have something like here. So go from here to there, not through this, okay, dashed line and then up, okay, but goes from here to there. All right. Okay. So CV equals to 3nR. So in that means we are looking at the constant volume process. So for constant volume, okay, so then let's see. Yeah, I kind of forget where is this term from. Let me see if CV over dt, CV times dt. It looks like it's from this guy here. If dt is equal to 0, then you have CV dt equal to minus p dv. Oh, right, I see. So for adiabatic process, okay, so that means there's no heat exchange. Okay, so from the definition, so then dq is equal to 0, right? So yeah, I remember where's that from. So dq equal to 0. So basically, there's one equation missing over here. So dq equal to 0, your dE is equal to minus dW. Okay, so dW you can always write as P times dV. Now for ideal gas, is equal to, so E internal is equal to this, or basically CV times T. So then dTE is equal to minus dV, or minus dW, okay? So this is where this is from. So it goes from equal to dQ minus dW, okay? So for adiabatic, this is for an adiabatic process. That means no heat exchange, okay? So this equal to that. Now for ideal gas, E is equal to 3/2 nRT, or CV C sub V times T. So then derivative of internal energy should be equal to CV dt, okay? So CV dt is this guy, equals to minus dW. So then CV dt equals to minus P dV, okay? For ideal gas, you can write P as nRT over V. So then this is minus nRT over V because of PV equal to nRT. Okay, so that tells you P is equal to nRT over V. Okay, so then your CV dt is equal to minus nRT over V. Okay, so this is for adiabatic process. Then we are going to go start from there. So starting from there, you can. So let's see. You are actually putting. So there's one step missing here again. Let me just make it up over there. Okay. So we then starting from CV dt equals to minus nRT over V dV. Okay. So you are moving T to this side. Okay. So that goes down there. You are putting this guy on the other end. Okay. So move this guy down here, CV times that. And then rearrange the term so you have dt over t plus nr cv, okay, times dv over v, that goes to 0. Okay, and for this you can do the integration to both sides, right? Integration there. Integration of 0 will tell you a constant. Okay, and then on this two term it's going to becoming natural logarithm of t, because this is dt over t. On this one, these three are constants. Okay, so then it's also nr over cv ln of v. Okay, so you get that. All right, so natural logarithm function here and natural logarithm function there. Now this guy can be rewritten as natural logarithm of v to the power of nr over c sub v, right? So then you have line of t plus that guy equals to constant. So then becomes line of t times this v to the power of nr over cv. Okay, that goes to constant. Now you do exponential of both sides to get rid of natural logarithm. So this is exponential of constant, which is still a constant. Okay, just a different constant number, but it's still a constant number. So the result will be t times v to the power of nr over cv, that is equal to constant. Okay. Now from PV equal to nRT, you can rewrite that T over V is equal to P over nR. nR is a constant, so it's P over nR. Okay, so T over V is equal to that. Okay, oh, let's see on the other side over here. Okay, now let's just leave this guy here, and then let's check on this other side over here. So CP is equal to CV plus NR. This is for an ideal gas. Okay, so then NR equal to CP minus CV. All right. So NR over CV, which is this power term here, should be CP minus CV over CV, which is equal to gamma minus 1. We write that gamma equal to CP over CV. Okay, so CP over CV. So that's gamma. All right. Minus 1. So that means T times V to the power of gamma minus 1. So this guy, this power is gamma minus 1, is equal to a constant. Or you can do T times V to the gamma divided by V. Okay, bring the minus 1 power as the denominator as V there. Okay, so then that equals to constant. All right, so now T over V, as this T over V here, can be written as P over constant. All right, so then P times V to the gamma is equal to constant. Okay, so this is the equation you can write for an adiabatic process. All right, in addition to the ideal gas law, for an adiabatic process, PV to the gamma is equal to constant. Okay, so that means P1 V1 gamma equal to P2 V2 gamma for that process. Okay, where gamma is equal to Cp over Cv. All right, the ratio of the constant volume heat capacity divided by the constant pressure heat capacity divided by the constant volume heat capacity. Okay. All right. So this is the equation you can apply when you see a adiabatic process. Okay. Now for an adiabatic process, let's take a look on the work done for that process. Okay. So again, for adiabatic process, there's no heat exchange, so delta Q equal to 0. So then derivative of E, internal energy, is equal to minus dW. Internal energy is 3/2 of nRT for a monatomic ideal gas. So then dW equals to minus 3/2 of R times dt. Okay, so this is from derivative of this internal energy. Okay, T is the variable. That equal to minus Cv dt. Okay, because Cv is equal to 3/2 of nR. All right. So then for work, okay, if you do integration of this side and then integration of this side, so that tells you work is equal to minus Cv of T final minus T initial, okay, because Cv is not a function of T. So then just take T final minus T initial, which means delta T. All right. Now T, you can solve it from the ideal gas law, PV equal to nRT. So T equal to PV over nR. TF will be PF VF over nR. TI will be PI VI over nR. Okay. So then that will be equal to minus Cv over nR because you have nR on both terms inside the parentheses there. Okay, so Cv over nR, PF VF minus PI VI. All right. Now remember, in the previous slides, we saw that nR is equal to Cp minus Cv. So then this is again equal to gamma minus 1. All right. So then work done for adiabatic process will be minus P final V final minus Pi Vi divided by gamma minus 1. Okay. Because this is inverse of that guy. Okay. nR over Cv is inverse of Cv over nR. So then this is equal to the difference of these two terms multiplied by each other divided by gamma minus 1. Okay. All right. So let's take a look on this one here. So it says monatomic ideal gas 0.5 moles at 400 kilopascal and 300 Kelvin expand quasi-statically until the pressure decreased to 160 kilopascal. Find the final temperature and volume of the gas. The work done by the gas and then the heat absorbed by the gas if expansion is adiabatic. Okay, so it tells you the expansion is adiabatic, and it asks you to find final temperature, T final or T2. Let me use T2 here. Volume, V2, work done, and then the heat absorbed by the gas. All right. Those are the ones we are looking for. So the heat absorbed by the gas should be 0, right? Because it says it's an adiabatic process. So that's something automatically you can figure out. Okay, Q is equal to 0. All right. Now let's take a look how to figure out T2 V2. All right, and then work. So the norms is M is equal to 0.5 mole. P initial is 400 times 10 to the third Pascal. K or T1 is 300 K. P2 is 160 times 10 to the third PA. So for an adiabatic process, so this is the ideal gas. So PV equal to nRT still applies here. All right. And then the other equations that, so P, also PV gamma, that's equal to constant. Okay. Where gamma is equal to Cp over Cv. Now there's a lot of information over here that's not directly given, but for monatomic ideal gas, Cp or Cv is 3/2 of Nr. Cp should be 5/2 of Nr. Okay, so then you can figure that gamma is 5/3. Okay, this is for monatomic gas. So I think I'm going to just list some of these equations, and then we probably don't have time to go through the full solutions. Okay, but you guys can get started here with those equations. So basically, you will be starting with these two, and then for the given norms. If you want to calculate work, we know that this will be P2 V2 minus P1 V1 over gamma minus 1. Was there a minus sign? Yeah, there's a minus sign there. So minus of that. So from those two, from this guy here, so basically you'll be writing like P1 V1 gamma equals to P2 V2 gamma, right? You are given, oh, no, you're not given V1, but you can figure out V1 by given those information using this equation, okay? Right. I think we are coming back tomorrow on this, okay? So we'll stop here.